Greetings, my young math Padawans. This is Chapter 4, Applications of Differentiation, Section 4.5, Limits at Infinity. Let's start off by looking at this function, 3x squared over x squared plus 1. I want you to notice a couple things about this function. The graph of it is over here on the left-hand side of your screen. And what I did was I looked at the table of values for this particular function. You'll notice I didn't number it conventionally. Instead, I went with some pretty big numbers or some pretty negative numbers and some pretty larger numbers. Here they go. And if you look at what happens to the actual function as my x values get closer and closer to negative infinity, you should notice that these values of the function go someplace. And as my x values go towards positive infinity, you should again see something happens to the y values. Did you say that those numbers were getting closer and closer to 3? Because if you did, that's right. That's exactly what's happening here, is both of these values are getting closer and closer to 3. As a result, in my graph, you should be able to identify what we're going to call a horizontal asymptote. So the horizontal asymptote is, by definition, exactly what that is. What happens as x goes towards infinity? Does my function level out, or does it keep growing? This particular function does, in fact, level out at 3. So if we take a look in your textbook's going to give this definition of a horizontal asymptote. And that's just pretty much what I just explained on the last slide. You don't need to necessarily copy that down, but just know that if I look as x goes towards either positive infinity or negative infinity and I get a value, a finite number, that's going to be a horizontal asymptote. Down here, these bottom two, these are some helpful limits to know and to remember. If you have a number over x to some power, the limit as x goes towards infinity is equal to 0. And as x goes towards negative infinity, if you have something that's in that same format, it goes towards 0. So I'm looking like, what if you were evaluating the limit as x approaches infinity of like 15 over x to the third power? That's 0. That's a no-brainer. We don't have to think about that too hard. Think about what's happening to the value on the denominator of this fraction as my x values get bigger and bigger and bigger. Well, 10 to the third power, 100 to the third power, 1,000,000 to the third power, that's going to become really large. And when you have the denominator of a fraction become really large, the whole overall fraction is actually getting closer and closer to 0. Two other things that are really helpful to know are the e to the x. The limit of e to the x as x goes towards negative infinity. So let me remind you, the blue line here that I'm drawing down on the bottom of this screen, that's the graph of e to the x. And if you look at what's happening as x goes towards negative infinity, that's going here to the left, you'll see that the function is getting closer and closer to 0. The other graph, e to the negative x, I'm going to draw that again, that's going to be over here on the left-hand side. E to the negative x looks like this. And as you can see, as x goes towards positive infinity with this graph, again, e to the negative x gets closer and closer to 0. So those limits exist there. Those are helpful to know in case you see those in different problems that we're going to do. Let's take a look at an example. The limit as x approaches infinity of 5 minus 2 over x squared. Well, let me remind you a little bit about how we can handle a limit. Remember, we can take this limit and we can split it up. So we can look at the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Well, the limit as x approaches infinity, let me back up. Remember, the easiest way to evaluate a limit is to actually plug in the value into my expression. Now, there is no x in my first part here. So the limit as x approaches infinity of 5 is exactly that. It's just 5. What about the second part? What about the limit as x approaches infinity of 2 over x squared? Again, remember, that's getting closer and closer. The bottom is getting bigger and bigger and bigger as x gets closer to infinity, which means that this is getting 2 over a huge number, which the bigger that number gets, the closer it becomes to 0. So my actual answer here will be whatever 5 minus 0 is, which is in fact just 5. What about the limit as x approaches infinity of 3 over e to the x? Again, the top is going to stay the same. It stays the same. But the bottom is going to get bigger and bigger and bigger, right? E to a power is going to become bigger and bigger the bigger the value for x is. So because the top is staying the same, but the bottom is getting bigger, there's not really much work here to do. The limit as x approaches infinity of 3 over e to the x is in fact just equal to 0 because that bottom is going to outpace the top and become bigger and bigger and bigger, and therefore the fraction will get closer and closer to 0. What about the limit as x approaches infinity of 2x minus 1 over x plus 1? Now you got to be careful. We can't just split things up, the way we might want to here. We have to be really careful. So we can look at the limit as x approaches infinity of the top, 2x minus 1, and we can look at the limit as x approaches infinity of x plus 1. And what we'll notice is we'll get, well, the bigger that is, 2 times a really big number is a big number. Minus 1 doesn't really matter. I get infinity on the top. What about the bottom? Infinity plus 1. Well, that's just infinity. So I end up with infinity over infinity here, which is no good. That's really bad. We actually call that an indeterminate form, if you want the really fancy term. I'm not worried so much about that, except I want you to understand that you can't do this problem. So instead, we have to go back to pre-calc rules. And we're going to try to find a horizontal asymptote, because again, that's what's happening as x goes towards infinity. So when we're looking at limits as x goes towards infinity or negative infinity of a rational function, right, a function that's written as a fraction, we're going to look at the degree. We're going to look at the degree of the top, and if the degree of the numerator, the top, is less than the degree of the denominator, the bottom, then the limit is 0. If the degree of the numerator is equal to the degree of the denominator, then the two things are equal. Then the limit is the ratio of the leading coefficients. You'll see an example of that here coming up. And if the degree of the numerator, the top, is greater than the degree of the denominator, the bottom, then the limit of the rational function doesn't exist. We don't have any horizontal asymptote. You might remember these from pre-calc. Remember, like, you would say m was less than n, and here we'd say m was equal to n, and here it would be m was greater than n. I don't know if that's ringing any bells to you or not, but you had these different inequalities that you would use to represent the degree of the numerator versus the degree of the denominator. Anyways, we'll get to that here in a minute. Let's look at this example again, that 2x minus 1 over x plus 1, the limit as x approaches infinity. Again, this is really just me finding the horizontal asymptote. And if you look, the degree of the top is 1, and the degree of the bottom is 1. And since the degrees are equal to each other, it's the limit of the coefficients, the numbers in front of the x. Remember, there's a 1 right there. So the limit as x approaches infinity of 2x minus 1 over 1x plus 1 is 2 over 1, which is just, in fact, 2. And again, that's because the degree on the top is equal to the degree on the bottom. Another problem, the limit as x approaches infinity of 3x squared over 4x squared minus 1. Again, the degree on the top is 2. I'm looking right here. The degree on the bottom is 2. These are equal to each other, so the limit is the leading coefficients, 3 over 4. That's the final answer. What about this guy? The limit as x approaches infinity of 4x minus 1 over 2x squared plus 5. Well, let's here, the degree on the top is 1, right? There's a 1 written right there, and the degree on the bottom is 2. So in this case, the top is less than the bottom. The degree of the top is less than the degree on the bottom. And what does that mean? Well, if we go back to that page, since the top is less than the bottom, we know the limit is going to equal 0. Again, if you think about it in terms of my problem, the bottom, the more bigger numbers I put in for x, the bottom is going to outpace the top because I'm squaring the bottom, but I'm only keeping the top, to the first power. What about this problem? 4x to the third minus 1 over 2x squared plus 5. The limit as x approaches infinity of that. Again, the degree of the top is 3. The degree of the bottom is 2. So in this case, the top is greater than the bottom. So for this particular problem, the limit does not exist. Or in other words, there are no horizontal asymptotes to this problem. I think it's really important for you to remember what a horizontal asymptote is and a vertical asymptote. So the limit as x approaches infinity or negative infinity, if I get a value when I look at those, it's a horizontal asymptote. And the limit as x approaches some individual number, if the result is infinity or negative infinity, that's a vertical asymptote. Typically, especially with rational equations, we think of this as where the function itself is undefined. Folks, that's all I have for you for today, so please take a minute right now. Make sure you took some pretty good notes. If you need a copy of mine, they're available online. But otherwise, here's your homework assignment, page 246 to 247, numbers 11 to 24. If you have any questions, don't be afraid to reach out. I'll talk to you soon. Thanks for watching.